Hi everyone. We're learning our lesson today is going to be on finding the slope of the tangent formulas for curves at a general point, and that's our learning goal. So after mathematicians found out a formula to find the slope of the tangent at a specific point, the next question they asked themselves was, what if you wanted to find the slope of the tangent to a function at places where x is 1, 2, 3, 4, etc., all for the same function, f at x? Would you have to use that first principles formula from yesterday every single time? Or can you find a general formula for the slope of the tangent of a particular curve at a general point, x f at x, and then use it to find the slope of the tangent anywhere on a curve? And the answer is yes, we can do that. The formula is called the derivative function, and requires us to use different notation to express the slope of the tangent. So this is said f prime at x, and it means the same as the slope of the tangent at a general point. So the slope of the tangent to a function y equals f at x at a point x f at x, also called the derivative function of f at x with respect to x, is given by the formula f prime at x equals the limit as h approaches 0 of f at x plus h minus f at x all over h. So this is our first principles formula for a general point. Okay, we talked about the origins of calculus, but now we're using first principles formulas for this chapter when we're finding the slope of the tangent at either a specific or general point going forward. So our first example says for us to find the formula for the slope of the tangent to the curve f at x equals x squared minus 4x minus 3 at any point on the curve. So we're going to use first principles. F prime at x is the limit as h approaches 0 of f at x plus h minus f at x all over h. So we're going to use a similar idea when we're finding f at x plus h. So for this function here, f at x plus h is going to be x plus h squared minus 4 times x plus h minus 3. And I just used the defining formula for f at x and replaced each x with x plus h. Now, if you can expand x plus h, great. It's, x plus h squared, it's x squared plus 2xh plus h squared. A little bit of a refresher would be to use FOIL here. And you can see that x times x is x squared. X times h is xh. H times x is also xh. So there'll be 2 of them. That's where you get the plus 2xh. And then h times h is h squared. So expanding a square of a binomial. And then distribute the negative 4 through here. And then see if there's any like terms for you to collect. In this case, there isn't. So now we're going to go back over here to our formula. And we can replace f at x plus h with what we just found. So that was x squared plus 2xh plus h squared minus 4x minus 4 minus 3. And then this minus in the formula here comes next. And since I'm subtracting f at x has 3 terms, I'm going to keep them in brackets, because I'm subtracting all of f at x, not just the term that happens to come first. And then that's all over h. And again, the reason I can't let h approach 0 is because then the denominator would approach 0, and you can't divide by 0. So the next thing I'm going to do is distribute that negative through the bracket here. So expand these brackets. So it's going to be minus x squared plus 4x plus 3. And we can see x squared minus x squared, that's a 0 pair. Negative 4x plus 4x adds to 0. Negative 3 plus 3 adds to 0. I think I had dropped an h here. This should be minus 4x minus 4h. Way over here, sorry guys. Minus 4x minus 4h minus 3. Minus 4h. Which means this is minus 4h. And this is minus 4h. And it should happen that way where, especially with polynomial functions, every term that's left should contain an h so that you can common factor out an h. Oops. So if I common factor out h from 2xh, I get 2x plus h from here minus 4 from here all over h. And now I can divide this h by this h and that gives me 1, or same thing as dividing top and bottom by h. They cancel out. So now my denominator is 1. It's safe to let h approach 0. So f prime at x is going to be, so if I let h approach 0, I'm going to get 2x plus 0 minus 4, so minus 4. And that's going to be my formula. That's going to give me the slope of the tangent anywhere I want along this curve. Okay, so that's the formula for the slope of the tangent anywhere. And if we look at part B, it says to find the slope of the tangent to that curve at the specific points where x is 1, x is 2, and x is 3. So when x is 1, we found the formula that f prime at x, which means the slope of the tangent anywhere along that curve, is 2x minus 4. So if I want to find the slope of the tangent when x equals 1, I'm just going to replace x with 1. Which means that f prime at 1 is going to be 2 minus 4 and negative 2, which means that the slope of the tangent is going to be negative 2. So let's look at our graph here. Find where x is negative, find where x is 1, and the slope should look like negative 2. So here's where x is 1 on the curve. That corresponds to this point here. And then you can see that it's going to have a negative slope. And does that slope look like negative 2? That would mean I would go down to right 1 or up to left 1. And that does look like that would be our slope of the tangent. There would be a tangent drawn when x is 1. With a slope of negative 2. Next, we want to find the slope of the tangent to that curve when x is 2. So f prime at 2 is going to be 2 times 2 minus 4, or 0. And we know that a slope of 0 is horizontal. So it's when x is 2. We're at the vertex there, or a valley, and you can see that the slope of the tangent is going to keep getting smaller until it gets 0 right here when x is 2, and then it's going to start to become positive after that. And then when x is 3, we'd find f prime at 3 is going to give us the slope of the tangent. when x is 3, and that's going to be 2 times 3 minus 4, or positive 2. And then at 3, so 1, 2, 3, we're right here. It's a symmetric point to this one, and this one had a slope of negative 2, and it makes sense that this would have a slope of the tangent of positive 2. All right, our second question. Given f at x is the square root of 2x minus 3, find f prime at x. Okay, so we're going to start with our formula. F prime at x is the limit as h approaches 0 of f at x plus h minus f at x all over h. And f at x plus h, I'm going to find, so f at x plus h is going to equal the square root of 2 times x plus h minus 3, or the square root of 2x plus 2h minus 3. And then the minus in the formula, f at x, which is the root of 2x minus 3, all over h. And again, I can't let h approach 0 because the denominator would approach 0. You can't divide by 0. So when we have radicals involved, our strategy has been to multiply top and bottom by the conjugate radical. In this case, the conjugate is going to be exactly the same first term here, or first radical, 2x plus 2h minus 3. Opposite sign in the middle. And then the exact same radical here. And then whatever we do to the top, we do to the bottom. And while we're still getting used to conjugate radicals, I'll write out all 4 terms. We're doing FOIL here. So each term in the first bracket is being multiplied by each term in the second bracket in the numerator. So I'm doing this times this, which is the root of 2x plus 2h minus 3 all squared. That just undoes the square root sign. This one times this one is just going to be, so positive and the plus 2 radicals multiplying together. Times radical 2x minus 3. And then multiply these two, so that's going to be negative this time, but the same 2 radicals multiplying together. And then the last multiplied together, a negative times a positive is going to give me a negative. And then they're exactly the same again, so this, I'm multiplying them by themselves, undoes the radical because we're squaring it. And then again, that's all over h. And these big yucky terms here, fortunately, add up to 0. And that's the beauty of multiplying by conjugate radicals, is now we end up with an expression in the numerator that doesn't have any radicals in it. Oops, I forgot here, the step by cautionary step here, the denominator does contain radicals. Don't forget to multiply bottom by bottom. Or you will get an answer that won't make sense for the question. It's always good to graph on Desmos and make sure that the slope that you get makes sense. We can see in part B of the question we're asked to find the slope of the tangent at a specific point. Okay, so back to the numerator again. Those middle terms add to 0. 2x I'll just expand that bracket through again while we're still getting used to this algebra here. So -1 times -3 is +3 over h times this conjugate radical here. And now we can see it 2x minus 2x, -3 plus 3, add to 0, and we're just left with 2h in the numerator, h in the denominator. We can divide out the h's. So now that problematic h is gone, it's safe to let h approach 0. As h approaches 0 in the numerator, I'm just left with 2. In the denominator, as h approaches 0, this term here approaches 0, so I'm still going to have the square root of 2x plus h from here, plus the square root of, 2x minus 3, my bad, because h is approaching 0, plus another 2x, square root of 2x minus 3. And so these are like, they're the same, which means there's 2 of them, 2 square root of 2x minus 3's, which means that these 2's divide out, 2 on the top, 2 on the bottom. Don't forget there's still 1 on the top. That's a common mistake that I see. Nope. So f prime at x is going to be 1 over the square root of 2x minus 3. You might be seeing some, or wondering some interesting things about what the function is we started with and what the derivative turns out to be, and we will see why all this is true in the next chapter when we learn the rules. So this formula again means that if I wanted to find the slope of the tangent anywhere along this curve up here, I just need to plug in the x value and into the derivative formula, and I should get the slope of the tangent. So then that follows for part B here. Find f prime at 2 and describe its meaning. So f prime at 2 is going to be 1 over the square root of 2 times 2 minus 3, or 1 over the square root of, 2 times 2 minus 3, which is going to be the square root of 1, which is just 1. And it means that the slope of the tangent is equal to 1 at the point 1. And then what if I needed to know the y value? I would use my defining equation for f at x, which was f at x equals the root of 2x minus 3, which means f at 1 would be the root of 2 times 2 minus 3, or the root of 1, which is 1. So let's look at our graph at the point 1, 1, and see if it makes sense that the slope of the tangent would also be 1 there, which means from this point I would go over 1, up 1, which doesn't touch the curve again, over 1, up 1, reverse it, and I should see that that looks like the slope of the tangent. It's always smart to check your answers on Desmos. It gives you a visual, so it always is connecting back to what it is you're doing, finding the slope of the tangent. Which is important. All right, so that is B, and then question 3. So it's a rational function. If y equals 1 over 5x minus 1, a, find the derivative f prime at x of the function. Describe what f prime at x means. And part B, find the slope of the tangent at the point when x is 2/5. So this is a graph of the function y equals 1 over 5x minus 1. And if we want to find the derivative, f prime at x, we're going to use our defining formula. F prime at x is the limit as h approaches 0 of f at x plus h minus f at x all over h. And f at x plus h for this equation is going to be 1 over 5 times x plus h minus 1, which is going to be 1 over 5x plus 5h minus 1. So f prime at x is going to be the limit as h approaches 0 of 1 over 5x plus 5h minus 1 minus f at x, which is 1 over 5x minus 1, and that's all over h, so we have this 3-layer fraction type of question, where we first get a common denominator in the numerator, and in this case it's not going to be a pretty one, it's going to be this polynomial multiplied by this polynomial. We'll leave it unexpanded. So if our common denominator becomes 5x plus 5h minus 1 times 5x minus 1, we have to create equivalent fractions by adjusting the numerators so we can subtract fractions. So I would have had to multiply the top by 5x minus 1 here, and I would have had to multiply the top by 5x plus 5h minus 1 here, and that's all over h. Now this is an important step here. I'm going to kind of combine some steps. I'm just going to write this top part here with one denominator. And I'm going to show subtracting the numerators, because that's what we're doing here. So I will have this minus to distribute through the bracket there. And that's all over h, which is the same as multiplying by 1 over h. So dividing by h is like multiplying by 1 over h, because you multiply by the reciprocal. The reciprocal of h is 1 over h. So now I've gone from a 3-layer into a 2-layer fraction. So if we look at the numerator here, multiplying by 1 doesn't change anything. I'm going to multiply that negative through the bracket. I dropped a 5 here. So make sure you saw that 5 there that I dropped. So that's minus 5x minus 5h, and it should be plus 1, because negative 1 times negative 1 is positive 1. All over, I'm going to put this h, the monomial term, out front, and then times 5x plus 5h minus 1 times 5x minus 1. And then see if there's any like terms to collect in the numerator. 5x minus 5x is 0, negative 1 plus 1 is 0. So I'm left with negative 5h in the numerator. And there's an h here, another monomial, so I can divide the h's out. And now it's safe to let h approach 0, because the denominator is not going to approach 0. So f prime at x is going to be, so in the numerator I'll have the negative 5. In the denominator I'll have 5x, minus 1. Because as h approaches 0, 5h approaches 0. And then times another 5x minus 1, not dependent on h at all in that bracket. Or, since these are the same binomial, I could write f prime at x is equal to negative 5 over 5x minus 1 all squared. So that's the derivative formula. So it says describe what it means. This formula will find the slope of the tangent to the curve f at x equals 1 over 5x minus 1 at any point x, bracket x f at x. So this formula will find the slope of the tangent to the curve f at x equals 1 over 5x minus 1 at any point x f at x. And then part B said to find the slope of the tangent at the point when x is 2/5. So we want to find f prime at 2/5, which is going to be negative 5 over 5 times 2/5 minus 1 squared, which is negative 5 over, so 5 times 2/5 is 10/5, which is just 2. 2 minus 1 squared is just 1. So therefore, m tangent is equal to negative 5 over 1, which is just negative 5. So then let's look where x is 2/5. So that's going to be 0.4, so about here. And we can see that if you find the corresponding f at x value, it looks pretty high up here. So it's going to be negative 5. It's definitely going to be negative and fairly steep, so negative 5 makes sense. Okay, so success criteria, I know what it means to find the derivative of a function using that formula, our derivative formula, and you can use the derivative formula to find the slope of the tangent at a general point, and then use it to find the slope of the tangent at any specific point. All right, so that is our lesson on slope of the tangent at a general point.